Okay, good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is a faculty in IIT Kharagpur. Okay, and this is the 9th week of 12-week course. Up to this point, anyone have any doubt? Because today we are going to discuss about statistical inference topic. So if anyone have any doubt, he or she may ask. Okay. Up to this point, like we have read about the probability, random variables, probability distributions, continuous and discrete probability distributions, like, and then descriptive statistics as well. These actually that are actually ABCD of statistics. Okay. Now we are going to use those topics to form sentence, or we can say that to use those concepts to infer, like to conclude something regarding the population, to estimate, to test hypothesis, something. Okay. So in this week, we will mainly discuss about the estimation of parameters. Okay. Statistical inference. Okay, so inference is actually means conclusion. Okay, we will conclude on the basis of some data. Okay, conclusion about some parameter or population. Okay, so mainly statistical inference are divided into two subcategories. The first one is estimation, and the second one is testing of hypothesis. Okay, in estimation part, there are two categories, and the first one is point estimation, and the second one is interval estimation. Okay, so like point estimation, when we estimate about the parameter and we provide only one value, like for example, like what is my height, and somebody says 6 feet. Okay, exact 0.6 feet, that means it is a point estimation. But in case someone says my height is around 5'5" to 6 feet, in between 5'5" to 5'6", then that is the interval estimation. Okay, and testing of hypothesis, like we gave some hypothesis or some statement about the parameter, and then check or accept or reject that statement regarding the parameter. That is called hypothesis testing. Okay, these are certain conditions, some some errors and something. We will discuss this later actually. Okay, today we will deal about point estimation. Okay, so point estimation, like for point estimation, there are various methods to evaluate or to estimate the parameters. Okay, and yes, before there, let us discuss about like what is parameter, what is parameters is actually like it is a function of population values. We can say that it is function of population values. Okay, it is in classical inference. We are going to discuss about the statistical inference, which is classical. It is a classical approach actually. Okay, in classical approach, parameters are like constants and unknown. Okay, so we will mainly try to estimate these parameters, which is nothing but the function of population values. Okay, now the second is statistic. It is statistic. The subject is statistics, but it is statistic. which is a function of sample values. Okay, it is a function of sample values, and our aim is we will use the different kind of statistics under certain condition for estimate some parameter. Then that statistic is called estimator. Okay, like we are going to discuss about or we are trying to evaluate population parameter, that is mean, suppose population mean. Then sample mean is used to estimate the population mean. Then that sample mean is actually an statistic, and that is used for estimating population. So it is a estimator. Okay, and okay, so there are more than one, like sample mean is also there, a sample median is also there to estimate like sample mean, population mean or population median. So there are different kinds of statistics. So there are some characteristics of a good statistics. Okay, there are mainly four characteristics. Like first one is unbiased, the second one is like consistency, the third one is efficiency, and the last one is sufficiency. Okay, so there are mainly four characteristics of an estimator. There are also, apart from this, there are like completeness of estimator. Okay, but we are mainly discuss about these four, and in this week we are dealing only unbiased and consistency. Okay, or consistent estimator. Okay, so what is an unbiased estimator? Like unbiased means there is no bias, there is no error, we can say. Like, okay, so when we estimate a population value, population function or parameter in short, okay, then the estimated value and the parameter value, if there is no difference, then there is no bias there. Okay, that means that is unbiased. Or in statistics, like suppose we have considered x1, x2 up to xn, there are n samples are taken from a function fx. Okay, it is a probability density function fx. It is a random sample. Okay, so these random samples are taken from this particular distribution. That is, it follows some distribution identically and independently. Word is already there within. Okay, so that means xi's are taken from fx distribution. It is IID distribution, IID random variable. Okay, then a function like suppose Tn, we define Tn as a function, okay, which is a like function of x1, x2 up to xn. Okay, it is a statistic. Okay, this is used to estimate the parameter. Okay, and if this like it is a okay, if like expected value of Tn equal to like gamma theta. Suppose we have a function of gamma theta. It is a parameter, function of parameter. We have considered the gamma theta. Then this Tn is used to estimate the gamma theta. If this condition holds for all theta belongs to the parameter space, then this Tn is said to be unbiased. Okay, then the Tn is said to be unbiased. If not so, then it is called biased. Okay, so either it is unbiased or biased. In bias, it is either positive bias or negative bias. Okay, And then, okay, the second one is consistency. Consistent is like, okay, the definition is like this. Suppose Tn, it is estimate and it estimate gamma theta. Tn minus gamma theta, the difference between the estimated value and the true value, okay, is less than epsilon. This property tends to 0. Okay, as it is a large sample property actually, consistency. Okay, so if the estimated value and the true value, the difference between the estimated value and the true value is less than epsilon, and where epsilon is some positive quantity, epsilon is some positive quantity which is greater than 0. Okay, and if this distance,
Sir, but
is
you have written greater than epsilon.
yes, that's why I have written pos 0, no probability. That is why I have written like epsilon is very small quantity. Okay.
But you have told less than, no?
Okay, less than, no. If so, then by mistake I am saying, okay, like it is the estimate. Okay, sorry. Let me revise it first again. Okay, then suppose we have considered epsilon. It is a very small quantity, which is a positive quantity. Okay, and this is the estimate. It is a estimated, yeah, or estimator, which is used to estimate this parameter. Okay, and this is the difference between these two. And if it is greater than epsilon, epsilon is already very small quantity, and it is greater than this probability is nothing. It is tends to 0 as n tends to infinity. Okay, this means this, or we can also say that like Tn, sorry, like Tn, which is a statistics, it converges to gamma theta in probability as n tends to infinity. Or we can say like this. It is a the definition of consistency. The estimated value or the estimator or the true value. The difference between these two is approximately 0. We can say like, okay, it is greater than 0. This probability is 0. That means it is not possible. Probability of any event is 0. That means it is not possible. And we are not going to equate it. We are tending to 0 as n tends to infinity. So this is called consistency. Like our estimate is consistent. That means it gives a solution, or it is the right solution. It converges to the true value. This is converging to a true value as n tends to for larger n. Okay, that means this. Or there is one more definition actually, like not actually definition, uh, some way to check the consistency of an estimator. Okay. Like if expectation of this, the estimator we are using to estimate the parameter gamma theta. Okay. Suppose this tends to gamma theta. Okay. As n tends to infinity. This is kind of unbiasedness condition, but it is not equal to. As n tends to infinity, the expected value of statistic converges to the parameter value. Okay, gamma theta. And the variance of that estimator tends to 0 as n tends to infinity. If these two conditions are satisfied for an estimator or for an statistic, then this Tn is said to be consistent estimator. Okay. This is the definition, or this is a sufficient condition to check the consistency of an estimator. Okay. Any doubt? If any, please ask. Okay. Now, these are actually some properties. Okay. These are actually some properties of a good estimator. Okay. Now, our aim is to estimate the values of the parameter. Okay. So there are different methods of estimation. Methods of estimation. So there are different methods. The first one is like method of least square. Method of moment estimator. And maximum likelihood estimator. These are the these are three topics which we'll cover in this week course. Okay, so method of moments estimator, in short we will call it MME, and maximum likelihood estimation. Okay, how to use these methods to estimate the parameter? Okay, we will discuss one by one. Okay, like in least square method, our aim is to minimize the error. The error is estimated value and true value. Okay, that is error. And we square it because it is maximum like least square, method of least square. Okay, method of least square. So in this, suppose for this method, actually, the first thing is for this method, our data will be like this: xi, yi, like in paired form. These are two different quantities, two different statistics, suppose height and weight, marks, expenditure, and like income and expenditure, any two things. Okay. And then our aim is to uh, model something, a model, like create a model which gives the relationship between these two. Okay. For example, yi equal to like alpha plus beta xi. Here, it is a linear model actually. Yi is some quantity which is dependent on xi in this. So in least square estimate, our aim is to evaluate these alpha and these beta. These are the parameters. Our aim is to estimate these values. Okay. And we are given data. With the help of those data, we calculate these values so that we can evaluate yi's on the basis of xi. Okay. And error term is also there, kind of. Okay. So, for example, like we can write our aim is to least square. Our aim is to minimize the least square. Okay, like least square method is like minimize the error. That means yi minus alpha minus beta of xi. This is our error term. We will denote it with the help of s and square term because it is a least square method. So our aim is to minimize this equation because this is the error. Okay. And for minimization or for optimization, we will differentiate these two. Sorry, not these two. We will differentiate equation star with respect to like alpha and beta. Okay. Because our aim is to find the alpha and beta. Okay. So first is like this, equate it to 0, and the second is okay. These two are called normal equation. Okay. So with the help in least square method, we will minimize the square of error. Okay. And this function, with the help of star equation, we find the normal equation, and then there are two equation in two variable. We will solve either analytically or numerical method. Okay. The second method is like method of moments. In method of moments, we compare sample moment to the population moment. Okay, like a non-central moment are compared with the sample moment. Suppose, for example, we have like x1, x2 up to xn samples. Random samples are considered from any distribution. Okay. Okay. So our aim is to like first we calculate the non-central moment, which is suppose it is a continuous distribution. We have taken integration, then x to the power j. This. Okay. This is the non-central moment. Okay. And we have these data sets or these random samples. Okay. So like alpha j, which is equal to 1 by n summation of xi to the power j. Okay. And this is called like sample moment. Okay. So in method of moments, we compare these two or equate these two and solve the estimated value of the parameter. Okay. If there is one parameter, we have mainly one sample value, two, we will consider two and further. Okay. The third is there are some properties actually. Sir has already discussed those things, so I'm not going to discuss. Just I'm trying to go to numericals. And the third is like maximum likelihood estimates. Okay, in maximum likelihood estimates, we first create a likelihood function. Okay, construct a likelihood function, then maximize that likelihood function. Okay, and that maximized value or that optimal value is our estimated value for the parameter. And for this purpose, we have again considered like x1, x2 up to xn. Let me write x1, x2 up to xn random samples are considered. It is drawn from some particular distribution, random samples, and the distribution will be like suppose this. Okay, so here these are random samples and this is our distribution. Okay, now the likelihood function, suppose we have considered theta as for parameter theta. Okay, so it is defined as like product of this PDF. Okay, why? Because it is already included. These are random samples. That means this is taken or drawn from this distribution identically and independently. Identically because all are like drawn from this particular distribution, and independently we have assumed that the samples are drawn independently. So likelihood function can be formed with the help of this. This is called likelihood function. Okay, now our aim is to find the value of the parameter at for which this function will be maximized. Okay, and for comfortable or for less, because wait, we have considered log likelihood to evaluate for the comfortable or less complexity of log. Okay, because it is a more complex nature. This log likelihood function is kind of a complex nature because it is a product of the PDF. So we have considered log so that it convert into actually summation. which is easy to deal with. Okay, so that's why, and log is an increasing function, so both have the same, both have an optimum value at the same value of argument or x. Okay, so we have considered this for simplicity or easiness. Okay, so this is our likelihood function, and then with the help of these likelihood function, we will again differentiate it with respect to the parameter and equate it to 0, and this is called likelihood equation. And again, with the help of these equations, we will solve the estimated value of the parameter. Okay, these are the simple calculus rule. Actually, we are given some function and we need to find the optimal value with the help of those equations. Okay, the only thing is we are dealing with like probability functions. Okay, and then I think these are the topics that is covered in 9.3. Okay, if anyone have any doubt, please ask. Okay, we will solve question, then we will definitely understand the like working rule of these methods. Okay, now from question 1 we will start. Here it is given x is a binomial random variable with parameter n and theta. Okay, like x follows binomial n of p it's theta. Okay, and Tn is a statistic which is x minus root n by 2 n minus root n. Okay, which of the following statement is or are correct? The first one is Tn is a biased. It is a biased estimator of theta, and the second is Tn is a consistent estimator of theta. For biased estimator, expectation of Tn, it is not equal to theta. We need to show this if it is biased. If it is biased, then we got this. That is biased. And the second, for consistency, we may either use the definition or we may use the two properties that are like expected value of Tn theta as n tends to infinity and variance of Tn. Tn is a function of samples, random samples. Variance of Tn equal to 0 as n tends to infinity. We need to check these two conditions to check whether the statement first and statement second is true or not. Okay, and for this start करते हैं. It is given that x follows binomial n theta. Okay, and for binomial we know that the expected value of x will be like n theta and variance of x will be like n theta 1 minus theta. We already know that, na? Like if x follows binomial np, then expected value of x equal to n into p, variance of x equals npq. So we have expected value of x and variance of x. Okay, now we take expected value of Tn, that is expected value of Tn, which is expected value of x minus root n upon 2 whole divided by n minus root n. Okay, now expectation is taken inside expected value of x minus expectation of any constant is expected value of suppose A, it is a constant, suppose. Constant is constant actually. Expected value of a constant is constant. So we may take like this, and n minus root n. Okay. Up to this point, it is clear, I think. Okay. Now, expected value of x, it is n theta. So from here, n theta minus root n upon 2, n minus root n. Okay. Now, if we take like n common, then we will get n, it's theta minus like 1 upon 2 root n. And in denominator, 1 minus 1 by root n. These two n's are cancelled out, and we will get like theta minus 1 upon 2 root n upon 1 minus 1 upon 10. Okay. This is expected value of Tn. Okay. These are expected value of Tn. So if it is not equal to theta, na, this is not equal to theta actually. It is clearly visible. It is not equal to theta. So that means what? That means it is biased estimator. If it comes out to be equal to theta, then it is the unbiased estimator. So this implies our expected value of Tn is not equal to theta. That means it is biased estimator. So the first one is correct one. Okay. We will now check the second. And for second, we need to check the consistency. Okay. And for this, we will check like expected value of Tn for large n tends to theta and variance of Tn equal to 0 for this. So it comes like as expected value of Tn equal to theta minus 1 upon 2 root n upon 1 minus 1 upon root n. Okay. So that means if we take n large, if we apply like limit, okay, then this gives theta minus it's 0, 1 minus 0, this equal to theta. Okay, that means for large n, expectation of Tn converges to the true value. Okay, that means first condition is satisfied here. Okay, now variance. So variance term will be like variance of is like variance of our Tn will be x minus root n by 2 upon n minus root n. That is x minus root n by 2 upon n minus root n. Okay, which will be written as like variance of x minus variance of some constant is 0, and these are constant which is multiplied, so it is like n minus root n whole square. You know that, no? Variance of ax equal to a square variance of x. Okay, so using the same logic or same rule, like this, and variance of x is n theta 1 minus theta, n theta 1 minus theta divided upon n minus root n whole square. We will take like n square is taken as common here, n theta 1 minus theta. N square is taken as common, it's 1 minus 1 upon root n. Okay, so after cancellation, it gives theta 1 minus theta upon n 1 minus 1 upon root n square. If we take large n here, if we take large n, then this is in denominator. That means it gives out to be 0 as n take to infinity. The second condition is also satisfied. That means for large n, expected value of Tn goes to parameter and variance goes to 0. That means it is also consistent. So both option A and B both are consistent. Both are correct. Okay. Anyone have any doubt? So please ask. Because we are doing nothing but using the definition and solve step by step. Okay, now second question will be like a random variable takes the value 1, 2, and 3 with probabilities. We are given 3 probabilities for 3 given values of random variables. Okay, with theta lies within 0 to 1. However, the observed frequencies are 1, 2, and 3 are like n1, n2, and n3. Then what is the MLE of theta? Okay, so we are going to use the maximum likelihood method. Okay, and for this, first we need to construct likelihood equations. So like we are given theta square, 2 theta 1 minus theta, and 1 minus theta whole square. These three are given for x equal to 1, x equal to 2, x equal to 3. Okay, these are given. Okay, so our likelihood equation will be with frequencies are also given actually. N1 frequency with N2 frequency with N3 frequency. These are in question. So our likelihood
X equal to 1 theta square, no sir?
Yes, it's theta square. Yes, it is theta square. Theta square, 2 theta 1 minus theta and 1 minus theta whole square. Okay, so our likelihood function will be like product of these three. Okay, so that means because it is partition in 3 different, so we have 3 product form, like it is from theta square. Okay, and the value of I from 1 to up to n1, because with frequency n1 it is theta square, and after n1 frequency, like suppose we have considered j from 1 to like n2, it is twice of theta 1 minus theta, and the third one is suppose we have taken it k from 1 to n3, and it is 1 minus theta whole square. So this is our likelihood function. Sorry, yes, likelihood function. Okay, now our second, first let us make it a compact form. It is a constant, there is no x is here, there is no x is here also and also. So that means it is theta a, it is not theta 2, it is theta square. Okay, so it is theta square n to the power n1 into twice to the power n2 theta to the power n2 1 minus theta to the power n2, and the third one is like 1 minus theta to the power n3. Okay, and the power n2 theta to the power 2n1, theta to the power n2. So it is written like 2n1 plus n2 and 1 minus theta to the power n2 plus 2n3. Can we write like this?
Yes, sir.
So this is our likelihood function. Okay. And we may directly differentiate this. Suppose this is equation star. We may directly differentiate this equation star and find the value of theta for which this L theta x is maximum. But for simplicity purpose, we've considered log. So taking log of both sides, it is like n2 log of 2 plus 2n1 plus n2 log of theta.
Sir, here you missed the 2.
Okay. And the third one is like n2 plus 2n3 log of 1 minus theta. Okay. Now differentiate this log likelihood function with respect to theta. We will get 0 plus 2n1 plus n2 upon theta plus n2 plus 2n3 upon 1 minus theta. Okay. So this is our log likelihood equation.
Sir, 1 minus theta is again differentiate.
It comes out to be minus 1. Okay, okay,
Minus
okay.
one.
Thank you. Thank you. Is it okay up to this point? Okay, now we will equate it to 0 actually. We will equate it to 0. Okay. So we will equate it to 0 and then because it is minus here, so we can write like this: twice of n1 plus n2 upon theta equal to like n2 plus twice of n3 upon 1 minus theta. We can write like this. Okay, then from here like 2n1 plus n2. Only we need to solve actually. We need to find out the value of theta in terms of n1, n2, and n3. 1 minus theta equal to n2 plus 2 n3 theta. Then from here like 2n1 plus n2 minus 2n1 plus n2 minus 2 n1 theta minus n2 theta, it's plus n2 theta equal to like n2 theta plus 2 n3 theta. Okay. Now again, we have considered like theta, then it comes out to be, okay, just take one more step. It's 2n1 plus n2 equal to theta n2 plus 2n3 plus 2n1 minus n2. Okay. And from here, like theta will be equal to 2n1 plus n2 divided upon here n1.
Minus and sir,
It is plus. It is plus. Okay. 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 Thank you. You're paying attention. Okay. It is 2n1 plus n1 plus n2 plus n2, that is plus 2n2 and plus 2n3, which is equal to 2n1 plus n2 and divided upon twice of n1 plus n2 plus n3. Okay. So this is our like MLE of theta. It's 2n1 plus n2 and it is twice of n1 plus n2 plus n3. Okay. So this is our maximum likelihood estimate. It is a general version. Okay. Suppose if we may like our question is like to calculate the MLE of theta and we have calculated. Suppose we have considered if n1 equal to n2 equal to n3 equal to n. In that case, theta cap will be equal to 2n plus n upon twice of n plus n plus n. This implies Tn upon 6n. This implies 1 by 2. In that case, our MLE will be 1 by 2. Okay. If we have given different values of n1, n2, and n3, we will put this value here and find the MLE of the theta at that condition. Okay. So next question. We are given 12 values. These are the sample from a, of size 12 from the geometric population having PDF this. This is the PDF of the geometric distribution. And then we need to calculate the estimate the theta using the method of moments. Okay, we are given sample. Okay, we are given sample and the PDF as well. Using with the help of method of moments, we need to calculate. So like fx will be given theta 1 minus theta x minus 1. I'm writing this. Okay, so in this case, in geometric distribution, the expected value of x, we already discussed it in previous classes. It is 1 by theta. Okay, we've already find out, which is also mu1 star. This is the first non-central point. Okay, so our expected value of x 1 by theta, and our like alpha 1 will be like 1 by n summation of xi, which is equal to 1 upon 12 because 12 things are given, and it is 4 plus 3 plus, we need to calculate, add all these things, plus 5, which is equal to 48. Sorry, it is not written here. Yes, 48. It's 48 upon 12. This comes out to be 4. That means alpha value equal to 4, and we will equate it with mu1, which is equal to 1 upon theta. And from here, theta cap method of moment estimator, which is equal to 1 by 4, is equal to 0.25. So the moment method of moment, with the help of method of moment estimate, the moment estimator will be 0.25 for these value of x. Okay. Now next question will be x1, x2 up to xn be a random sample from uniform 0 theta. Okay. If these are the ordered statistic, we will denote x within bracket 1, x within bracket 2. These are ordered x1 less than or equal to x2, less than or equal to xn. Then which of the following statement is or are correct? Okay. Again, like xn is the MLE of theta and xn is the consistent estimator of theta. Okay. So for first, we are given fx equal to 0 to theta. That means it is 1 by theta for x lying between 0 to theta. Okay. So first we will make likelihood equation, which is equal to product I from 1 to, since we are n random variables, so 1 by theta, it comes out to be 1 by theta to the power n. We may take like log of likelihood, which is equal to 0, that is log 1 equals to 0 minus of n log of theta. Okay. Now differentiate this log of L theta with respect to d theta. We will get minus n upon theta and equate it to 0. From here we get theta equal to minus n upon 0. So this is not applicable because with the help of the usual method, the MLE method, we are not able to find the MLE because here the support x depends on theta. And in usual method, the assumption is that like the support is independent of the parameter. Here, support or this x is called support. Support is dependent on like parameter. So this method is not useful. So our aim is to actually what? Our aim is to maximize this equation number 1. Na? And it is clearly mentioned because theta is greater than 0. Okay, theta is greater than 0, n is a positive quantity. That means as the n is smaller, the for large value of n, like it is minimum. So smaller value of n gives the larger value of equation 1. Okay, so that means
Excuse me, sir.
yes.
So the larger value of theta or n?
Oh, okay, wait. Here we need to like what? We need to maximize the L theta x function. Okay, so that means what? Suppose we fix one value. Suppose we fix the value of theta, or we fix the value of n. Okay, suppose for n equal to 1, the value of theta, as the value of theta increases, the likelihood value decreases. Okay, for a fixed value of n, if theta increases, that means the value decreases. The smallest value of theta gives the larger value of equation 1. Is it clear?
Okay.
Yes, sir.
And
Inversely proportional.
exactly. And also here, it is ordered statistics. It is clearly given. Now, we can write like this, na? Like 0, x1, x2, xn, theta. It is given now. It is given here clearly. So now the value of theta is what? Can anyone tell me? Because the smaller value of theta gives the larger value of this. So the smaller value of theta will be
Xn.
can anyone?
Xn.
Exactly, because the theta is greater than or equal to xn. So the minimum value of theta is xn. So that means the MLE of theta is this. Maybe some people thought x1 is the smallest value among these. No, our aim is to find the value of theta for which this likelihood function is maximum. And the smallest value of theta is nothing but xn, which is smaller than or equal to theta. So from here, we conclude that the MLE of theta is xn. Okay, the supremum value of the random sample. Okay, so this is our maximum likelihood estimate. That means our first xn is the MLE of theta. It is psi. This option is correct. Now the second is again xn is the consistent estimator of theta. So for consistent estimator, like okay, for consistent estimator, expected value of xn goes to the parameters itself as n tends to infinity, and variance of xn goes to 0 as n tends to infinity, or for larger value of n. Okay, so the xn is like this, na? Because we are using ordered statistics. So this is the notation for ordered statistics. So first, we need to calculate the expected value of xn and variance of xn. And before calculating this, we need to find the like we need to find the distribution of xn, na? Because in ordered statistics, the larger or the maximum of xi has a different distribution. The minimum, the joint, the marginal, everything has a different kind of distribution. Okay, and for larger case, suppose like let x1, x2 up to xn follows fx of x, and the CDF is capital Fx. Okay, then x1, x2, xn, these are ordered statistics. Then xn, the PDF of PDF of xn, that is, suppose I have donated like this, for example. Okay, this is the PDF of the maximum of xi. Okay, or xn. This is like equal to n fx of fxn of x, like power n minus 1 and fxn by x. Okay, this is the PDF for largest value of xi. So here n equal to n, and we are given uniform distribution. Okay, x follows uniform 0 theta. So fx equal to 1 by theta, and the capital Fx of x equal to like x by theta. Okay, these are already discussed. Okay, this is the PDF of uniform distribution. This is the CDF of uniform distribution. Okay, so it's x upon theta to the power n minus 1, and it is 1 upon theta. So it is like n upon theta to the power n, x to the power n minus 1. So this is the PDF of xn. This is the PDF of xn. Now our next aim is to calculate the expected value of xn and variance of xn. So the expected value of xn will be like xn, that is x, into x upon, we may write like xn here. Here write xn, here write xn, here like xn. These are just a sample which represent the maximum value of xi. So we may use x, not xi or xn. Dx. Okay, and the range of this is 0 to theta. So it is n upon theta to the power n, integral over 0 to theta x to the power n dx, which is n upon theta power n. It is x to the power n plus 1 upon n plus 1, 0 to theta, and this is n upon theta to the power n, theta to the power n plus 1, and it is n plus 1. So from here, we have found out expected value of xn is n upon n plus 1 theta. Okay. And similarly, like here we can like see that. Oh, okay. Wait. Or we can write this like this, na? Like theta n theta upon n 1 plus 1 by n. That is theta upon 1 plus 1 by n. We can write like this. So limit n tends to infinity, xn equal to this comes out to be theta. That is the first property of consistency is proved or it holds. Now variance of xn, which is expected value of xn minus expectation of xn whole square. So now we will calculate this and then the variance of this. So expected value of xn square equal to expected value of xn square equal to like again 0 to theta x square, and it is our n theta n upon theta to power n x n minus 1 n upon theta to power x n minus 1 dx, which is n upon theta n 0 to theta, it is x to the power n plus 1 dx. From here it is n upon theta power n plus 2 upon n plus 2 0 to theta, which comes out to be n upon theta to the power n into theta to the power n plus 2 upon n plus 2. So the expected value of xn square comes out to be like n upon n plus 2 theta square. Okay. Now variance of xn, using this relation we will find out. I am writing it directly actually. Okay, the variance of x will be like n theta square upon n plus 2 n plus 1 square. Okay, so this is our variance. Now we can write this n theta square upon n 1 plus 2 upon n, and n square 1 plus 1 by n square. Okay, so this comes out to be like theta square upon n square 1 plus 1 plus 2 by n and 1 plus 1 by n, and this comes out to be 0 as n tends to infinity because here it is n square. So that means second property also satisfies. So that means xn is a consistent estimator of theta as well. So both options are correct. Clear up to this point, na? Okay. Now next question will be like, let y equal to a plus bx be the regression line of y on x based on the given points. These are 3 points. We need to calculate the value of y at x equal to 2. Okay. So it is regression line as given already. So like xi, yi. Xi is 1, minus 2, and 3. Yi will be like 1, minus 1, and 2. Okay. And yes, in this case, the estimated value of a and b will be calculated with the help of this formula, like it's summation of yi minus b summation of xi whole divided upon n, and the b estimate will be like n summation of xi yi minus of summation of xi summation of yi whole divided by like n summation of xi square minus summation of xi whole square. Okay, like in method of least square method, we have when we minimize the least square, then the estimate for real line is like this. Okay, so we need to calculate summation yi, summation xi, summation xi equal to 4 minus 2, it's 2, summation summation it is 2, it is 2, xi is also there, so xi yi 1, it is 2, it is 6, it comes out to be 9, summation xi square 1, 4, 9, it is 14. Okay, so a cap summation yi, which is equal to 2 minus b into, okay, we need to first calculate this, then in this condition. B cap equal to like n. Here n is given 3. N is given 3 into summation xi yi, which is equal to 9 minus summation xi into summation yi, which is equal to 2 into 2 divided upon 3 summation xi square, which is equal to 14 minus summation xi whole square, which is equal to 4. And it is 27 minus 4 upon 42 minus 4, which is 23 upon 38. So this is the value of B, the estimated value of B. Now A cap will be summation yi, which is 2 minus B, which is 23 upon 38 into summation xi, which is 2, and whole divided upon n, which is equal to 3. So 2 minus 46 upon 38 whole divided upon 2, 38. It's 76 minus 46 upon 38 into 3, and it comes out to be 30 upon 38 into 3, which is equal to 10 into 38, which is equal to 5 into 19. Okay, so these are our values of A and B cap. So our regression line will be A plus B, 23 upon 38x. Okay, now for the second thing is we need to calculate the y for x equal to 2. So y at x equal to 2 will be like 5 upon 19 plus 23 upon 38 into 2, which is equal to 5 upon 19 plus 23 upon 19. It's 2 divided by this. So it comes like y at x equal to 2 is 5 plus 9, it's 28 upon 19. This is our final answer. Okay. Now the next question is, if x1, x2 up to xn are IID normal with mean mu and variance sigma square, for what value of k will this be an unbiased estimator of sigma square? Okay, again, so if t is an unbiased estimator of sigma square, then expected value of t must be equal to sigma square. Okay, so okay, let's start then. Here we are given like xi follows normal IID normal mu sigma square, and that means expectation of xi or x1 or x2 or this, it's mu, and variance of xi is sigma square. Okay. And Next is, okay, here we are the whole square term. That means if we expand, we have xi square, xi plus 1 square, and the square term is there also. So, okay, now the expectation of xi square is equal to what? It is variance of xi square. Okay, not xi square, why? Variance of xi minus expectation of xi whole square. This is the relation. Okay, so it is sigma square plus mu square. Okay, these two. Now T equal to k upon n minus 1 summation of xi plus 1 minus xi whole square, which is equal to k upon n minus 1. It is a minus b whole square term. That means uh, like xi plus 1 whole square that means xi plus 1 whole square plus xi whole square minus twice of xi plus 1. Okay, a minus b whole square. Now there is summation from 1 to n minus 1. Okay, that means it is k upon n minus 1. And when we take n, then it is, we have taken summation over this, and this. Okay, so the first one will be like x2 square plus x3 square up to xn square, because it is xi plus 1 and I from 1 to n minus 1. And the second will be like x1 square plus x2 square up to n minus 1 square plus x minus twice of x1 x2 plus minus twice of x1 x2 plus x2 x3 plus xn minus 1 xn. Okay, so like here there is n minus 1 terms, here there is n minus 1 terms, and here it is also n minus 1 terms. Okay, now we will consider the expectation. Expected value of t, which is expected value of this quantity. So k upon n minus 1 is taken outside. Expected value of these quantities will be like expected value of x2 square plus x3 square plus xn square plus expected value of xn square plus x2 square plus x minus 1 square and minus of twice of this quantity. Here it is given IID, that is independent and identically distributed. And we know that if it is independently and identically distributed, then in that case, we may write like this. Na? Expected xi equal to expectation of x into expectation of y in case of independent. Okay, so this is expectation of x1, x2, expectation of x2, x3 into, that can be written as expectation of x1 into expectation of x2 plus expectation of x2 into expectation of x3 plus expectation of this. Let me write like this again. Okay. Now expectation of x2 square is here, expectation of xi square is this for all I, because it is identical as well. So that means k upon n minus 1. It is sigma square plus mu square for first. Second one is also for sigma
Excuse me,
square
sir.
plus, yes.
Mu square, not mu2.
Okay,
Mu
okay, sorry,
square.
sir. I am telling mu square, but I think mu2. Sorry, mu square. It's mu square. Okay, up to n minus 1 times. Okay, plus again x1 square plus x2 square plus xn minus 1. Same like sigma square plus mu square plus up to n minus 1 times again. Okay, and the last one is like twice of expectation of x1 into expectation of x2. Expectation of x1 is like mu square sigma square. Okay, you see it is mu, expect mu and expectation of x2. Okay, wait. I think I'm a little bit confused. Mu square plus mu square. Okay. Expectation of x1 into expectation of x2. And both have mu. So it is twice of, twice of mu square plus mu square up to, it is also n minus 1 times. Okay. So that means what? That means k upon n minus 1. And it is n square plus mu square. So n minus 1 of sigma square plus mu square plus n minus 1 times of sigma square plus mu square and minus twice of n minus 1 of mu square. Okay. So from here k upon n minus k. So it is like twice of n minus 1 sigma square plus mu square minus twice of n minus 1 mu square. Okay, so mu square will be cancelled out. That means it comes out to be k upon n minus 1 twice of n minus 1. N minus 1 is also cancelled out actually. So it comes out k into 2 into sigma square, that is twice of k of sigma square. Okay, and if it is unbiased estimator of sigma square, that means the expected value of Tn, it is Tn or something else. It is T only. The expected value of T is sigma square, which we calculate twice of k of sigma square, and from here k equal to like 1 by 2. So the value of k for which this T will be an unbiased estimator of sigma square is 1 by 2. Okay. Now the next question is like, given the observations, they're given 4, 5, 7, 8 observations are given from the uniform distribution with parameter with range theta minus 0.2 to theta plus 0.8, with theta lies between minus infinity to plus infinity. We need to calculate the MLE of theta again. Okay, So first of all, the PDF of x is, it's 1 upon theta plus 0.8 minus theta plus 0.2 comes out to be 1 for x belongs to theta minus 0.2 to theta plus 0.8. Okay, this is our PDF. For ML estimation, here again the support lies or depends on the parameter itself. So that method is not we will use. Okay, it is already given here. So the x will be what? Like theta, sorry, it is like theta minus 0.2. And the minimum value of these are, like the first one is this 0.71. We may write again ordering the sample values. Okay, then it is 0.8, then it is 0.88, 0.9, 1.2, 1.62, 1. Okay, think 1.2, 1.4, then 1.62, then 1.68, and then theta plus 0.8. Okay, for this. Now again here, from here, theta minus this must be less than this, and from here also theta plus this must be this. Okay, so from these two relations we have got the value of theta. From like first, theta minus 0.2 is less than 0.71. This implies theta less than 0.71 plus 0.2. So theta cap will be like 0.91. Theta cap must be less than 0.91, and 1.68 less than theta plus 0.8. From here, like theta is greater than 1.68 minus 0.8, that gives okay 0.88. Okay, so that means the value of theta lie within greater than this quantity and less than this quantity, so that theta cap lies between 0.88 to 0.99. Okay, so any value within this range is the MLE of theta. Okay, any value within this range is the MLE. That means MLE is not unique. That means MLE is not unique. We can also draw this inference from this question. Okay, now our question is still remain. We need to calculate the value of this. Na? So the MLE will be like this. Here, any value. So like we may take the mean value 0.88 plus 0.91 divided by 2. That gives to be 0.83.15, that is 895, which is approximately equal to 0.90, which is this quantity here also. So the MLE of the theta for these random samples will be 0.9. Okay. That means the likelihood function is maximized at 0.9. Okay. So next question will be, if x1, x2 up to xn be a random sample from PDF is, then what is the MLE of theta? Okay, here support is independent of parameter, so we can use the usual method. So that means the likelihood function will be like product of I from 1 to n f of xi, that is product of I from 1 to n, theta plus 1 to the into x power theta. That means theta plus 1 to the power n and product of xi power theta. Product of xi power theta. I think, okay. There is a mistake here. We write like this, product of xi power theta. Okay. So product of x1 power theta into x2 power theta. Now again, taking log. So that is log of L theta, which is equal to n of log of theta plus 1 plus summation of theta log of xi. Okay. Now differentiate this likelihood function with respect to theta. We get n upon theta plus 1 plus of summation log of xi. Okay, and equate it to 0. We will find out like summation of log of xi equal to minus of summation of theta plus 1. Okay, from here theta cap will be our minus of n of summation of log of xi, and then okay, minus 1 is also there, I think. This. I think it is right. Hello. Okay, let me check once. Log of this. I think it is right. No? If so, the MLE of theta will be like this. Okay. The next question will be, if x1, x2 up to xn be a random sample from a Poisson population with mean lambda, then what is the MLE of log of lambda? Okay. So again, we are given it is a Poisson process. That means so our PDF will be like e to the power minus lambda, lambda to the power x upon x factorial. Okay. For x 0 1 up to infinity. So our like log likelihood function, it is like product of this e to the power minus lambda, lambda to the power x upon x factorial. Okay. It is xi actually. So it is e to the power minus of n lambda. Okay, plus xi log of lambda. Sorry, I have not taken log as no? It is lambda power summation xi. Okay, I think I'm doing something mistake considering both simultaneously. The first is multiply these terms, e to the power minus of n lambda, lambda to the power summation of xi upon product of xi factorial. Okay. Now we have taken log of L. that is e to the power minus, that cancel out, it is minus of n lambda plus of summation of xi log of lambda minus of summation of xi factorial. Okay.
The, the log
Log
summation log.
log of xi. Okay. Now, now our aim is to differentiate this. So the next step is like log of L upon, it is minus n, it is plus summation of xi upon lambda. It comes out to be 0 because there is no lambda here, and equate it to 0. We will find out lambda cap equal to its summation of xi upon n, which is nothing but x bar actually. Okay, so we have calculated the MLE of lambda, which is equal to x bar. But here we need to calculate the MLE of log of lambda. Okay, so there is an invariance property of lambda, invariance property of MLE. Invariance property. Okay, so invariance property state that suppose, let me write it, for a given, like suppose if t is the MLE of theta and like psi t is a 1 function. Okay, then psi of t is MLE of sine of theta. Okay, this is the invariance property. That means if t is MLE of theta, then psi t, any function of t, is 1 function. Then psi of t is MLE of sine of theta. So with the help of this, and log lambda is a 1 function. So using invariance property, like MLE of log lambda equal to log of MLE of lambda, that is log of r. This is our answer. Okay. Now the next question is, a sample population is drawn from the population gamma with parameter alpha and beta, and the value of first and second sample moments about origin are 10 and 150 respectively. Then what is the estimator of alpha and beta obtained by the method of moments? Again, method of moments, we are given the PDF like fx of x, it is gamma, that is beta to the power alpha upon gamma alpha, e to the power minus beta x, x to the power alpha minus 1. Okay. Now we need to find its non-central moment, first and second non-central moment, and equate it with the sample moments. So we already know that actually, like expectation of x is 0 to infinity, x into beta to the power alpha upon gamma alpha, it's e to the power minus beta x, x to the power alpha minus 1. Although we know that in case right here, x follows gamma alpha beta, then expectation of x is alpha upon beta, and variance of x is alpha upon beta square. already know this. We have already discussed it, but let me write it. It's beta to the power alpha upon gamma alpha, and it is like e to the power minus beta x to the power alpha x. Now it is what? It is our gamma function. Na? It is our gamma function. 0 to infinity e to the power minus beta x to the power alpha dx, and it comes out to be like if it is right in the general version, let me first write it. It is suppose like x to the power n minus 1 e to the power minus ay. It is gamma n upon a to the power n. E to the power upon gamma n. Yes, it is gamma n upon a to the power n. Okay. So with the help of this, we may write like this: beta to the power alpha gamma alpha, and it can be like it is alpha plus 1 minus 1. Okay, and it's divided upon beta to the power alpha plus 1. So it comes out to be alpha upon beta. Okay. In a similar manner, we can calculate expectation of x square and then variance of x, which is equal to this. So we may directly use expectation of x square equal to variance of x minus expectation of x whole square, which is alpha upon beta square minus alpha square upon beta square, which is alpha 1 minus alpha upon beta square. Okay, now we are given the sample moments are 10 and 150. That means alpha upon beta equal to 10 and alpha 1 minus alpha upon beta square equal to 150. They're given these. Okay. So from here, alpha equal to 10 beta, and we will use like 10 beta 1 minus 10 beta upon beta square is equal to 150. Okay, from here like 10 minus it's 100 beta upon beta equal to 150. From here it is 10 minus 100 beta equal to 150 beta. It's 250 beta equal to 50 beta equal to 10. From here beta equal to 10 upon 250. That means beta can be calculated or estimated like 1 upon 25, that is 0.04. Okay. Now putting the values of beta, that is 1 upon 25, alpha equal to 10 into 1 upon 25, it is equal to it's 2 upon 5 or 0.4.
Excuse me, sir.
Yes.
Sir, I
Oh,
think there's some mistake in value of beta.
beta. Okay. Okay. I think alpha upon beta is 10. It is given here. and alpha 1 minus alpha.
Then
Okay,
beta
let me
cap, the
check.
value of beta.
Value of beta. Okay, let me check. So here alpha 1 minus alpha equal to 150 upon beta square. Okay, alpha equal to 10 beta. From here we put this value here. Okay, so that is 10 beta. 1 minus 10 beta upon beta square equal to 150. So it is 1 beta will be cancelled out. It is 10 minus 100 beta upon beta equal to 150. Up to this point it is okay. Hello.
Yes, sir.
Okay, up to this point it is okay. So it is minus na. That means it is 150 beta plus 100, that is 250 beta equal to 10. So that means beta equal to 10 upon 250.
Okay, sir. Okay, sir.
Okay. If there is calculation mistake, you may check. Okay, the process is same, and I think calculation is also right. But if it is, then check it. Okay, so the value of beta is this, and the value of alpha is this. Now, the question 11th is, if x1, x2 up to xn constitute a random sample of size n from a population given by this, then what is the estimator of theta by the method of moments? Again, so here,
Excuse me, sir.
yes, yes, yes,
No.
yes,
Sir,
yes.
in the previous question, the value of expectation of x square is there's some mistake here. Variance of x plus expectation of x square.
Okay, okay, okay. Thank you. It is plus, na? It is also plus. Then it is also plus. Then it is also plus. Then it is also plus. That means it is 50. Okay. That means it is 50 beta equal to this, and it is 10 upon 50. That is 1 by 5 or 0.2. And again, alpha equal to 10 into x 1 by 5. Then alpha cap equal to 2. Is it okay now?
Yes, sir.
Okay, thank you. Okay. The next question will be like, they are given a random distribution, this twice of theta minus x upon theta square. We need to calculate the method of moment estimator for theta. Okay. So again, alpha 1 sample 1 by n summation of xi, which is also called x bar. Now mu1 s, that is integral over 0 to theta x into 2 into theta minus x upon theta square dx, which is 2 upon theta square integral over 0 to theta x minus x square dx, which is equal to 2 upon theta square theta x square upon 2 minus x cube upon 3 0 to theta, which is equal to 2 upon theta square. If we take the value of theta, it is theta cube upon 2 minus theta cube upon 3. So mu1 dash equal to 2 upon theta square. It is 6, 3 theta square minus 2 theta cube. It's square, it's also cube. So theta square, theta cube, it's 2 minus 1, that is 2 upon theta square. It is theta cube upon 6. and the mu1 prime or mu1 dash will be it's theta upon 3. Okay. Now equating alpha cap equal to this implies alpha cap is x bar equal to theta upon 3. From here, theta cap, that is method of moment estimator, equal to psi of r. Simple. Okay. The next question is like, if x1, x2 up to xn are IID random variable, then find expected value of this nx bar square upon n minus 1 minus capital S square, where S square is sample variance. Okay. Now our question will be like this. Okay. So first expectation of this, expectation of S square, which is expectation of this. So like we need to calculate expected value of nx bar square upon n minus 1 minus of S square. That means we need to calculate n expectation of x bar square on n minus 1 minus expectation of S square. Okay. Although we may know this is a capital S square, which is an unbiased estimate of sigma square. Okay. So that means it is sigma square, but we will check is this an expectation of x bar square. Okay. We are given n samples. So in properties, like if xi follows normal sigma square, xi minus mu upon sigma, which is equal to z, follows normal 0 1, z square follows chi square 1. It is clear. This is the definition of chi square variance. So and also like x bar follows, in that case x bar follows normal with mu and sigma square by n. These are the property of normal distribution actually. Okay. So now from here, like x bar follows normal mu theta is like mu equal to theta square by n. Okay. And expected value of x bar equal to theta, variance of x bar equal to theta square by n. That is expected value of x bar square equal to theta square by n plus theta square. Okay. Now the second is expectation of S square. S square is xi minus x bar whole square. Okay. So from there, summation xi minus x bar upon sigma whole square. This quantity chi square 1 summation I, then chi square n minus 1. Okay. So this implies here it is actually theta square, or theta not square actually. This follows chi square n minus 1 degree of freedom. Okay. Xi minus x bar upon theta follows chi square with n minus 1 degree of freedom. If it is mu, then it is n degree of freedom. It is x bar, which is a sample value. So it is 1 minus the degree of freedom. It is n minus 1 degree of freedom. Okay. So it follows chi-square n minus n minus 1 degree of freedom. So that is expected value of summation of xi minus x bar on theta square. Also, if like I square n, then expected value of w equal to n and variance of w equal to twice of. So with the help of this, the summation is from 1 to n. So the expected value of this is n minus 1. Okay. So if 1 by n, we divide 1 by n from here, so it is nothing but 1. So our next aim is like sorry, it is, we have got this quantity is here, and the expected value of 1 by n is our, it comes out to be a 1 by n summation xi minus x bar, it is theta square. Na? Yes. From here it is like 1 by n minus 1. Expectation of summation of xi minus x bar whole square. Theta square. Okay. And this is our S. So it comes out to be this. Now we need to calculate this quantity, which is n upon n minus 1. N upon n minus 1 expectation of x square, which is minus expectation of x square, which is n upon n minus 1 expectation of x square theta square upon n and n plus 1 by n. Okay. So we may write like this, n plus 1 by n and then theta square minus, sorry, yes, minus, it is theta square. So it comes out to be n upon n minus 1 and plus 1 upon n. I think I have missed something here because my answer is not matching. Wait, let me check. Need to find out this quantity. Okay, this can be written as this. So this quantity is correct. I think n should be cancelled out and our answer will be like n plus 1 upon n minus 1 theta square minus theta square. Okay. Here is something mistake. Expectation of this 1 by n, 1 minus theta square equal to this. Find the value of this. Okay, I think this is the answer actually. Okay, maybe find this. Okay, if it is n plus 1 of theta square minus of n minus 1 of theta square. And from here, it is like n theta is is like theta square n plus 1 minus n plus 1 upon n minus 1, which is 2 of theta square upon n minus 1. Okay, so we need to calculate the value of this. There, this is this. So and it calculated as 2 theta square upon n minus 1. Okay, I think there is some mistake here, but you people may see. Okay. Now the next question will be, suppose a random sample of size 2 was selected from a population with the PDF. Yes. Find the MLE of theta. Okay. So the PDF will be twice of theta minus x upon theta square. And since we are only sample of size 2, so that means our likelihood function will be twice of theta square, theta minus x1 into twice of theta square, theta minus x2. Okay. And it is written like 4 upon theta to the power 4, theta minus x1, theta minus x2. Okay. To this point, it is clear. Now, taking log, it is like log of 4 minus 4 log of theta plus log of theta minus x1 plus log of theta minus x2. This is our log likelihood function, and differentiate log likelihood function with respect to theta, we get 0 minus 4 upon theta plus, okay, not log here, it is 1 upon theta minus x1 plus 1 upon theta minus x2 and equate it to 0. Now our aim is to find the value of theta. So from here, 1 upon theta minus x1 plus 1 upon theta minus x2 equal to 4 upon theta. Okay, so it is like theta minus x1, theta minus x2 comes out to be theta minus x2 plus theta minus x1 equal to 4 upon theta. And from here, it is like theta square plus x2 theta plus, it is 2 theta square minus x1 theta is equal to 4 theta minus x1 theta minus x2. Okay, we need to separate the theta from x, because x is a sample value. So we need to multiply this also, 4 theta square minus theta of x1 plus x2 and plus x1 x2. So from here, it will be like 4 theta square, 2 theta square, 4 theta square minus 2 theta square. It is theta, it is theta, it is theta. So it is plus theta. Okay, so it is x1 minus x2 minus x1 plus x2. Okay, theta x1, theta x2. Okay, and plus x1 x2 equal to 0. This implies 4 2 theta square plus x1 x2 equal to 0. And from here, like theta square equal to minus of x1 x2 upon 2. Okay, again there is some mistake. Okay, minus of this x1 minus x2 minus x1 minus x2. Okay, okay, minus x2 is there, na? Yes, yes.
So,
It comes out to be like
minus x1 plus x2. Then only
it is minus x1 minus x2 is there, na?
yes. Sir.
Because is
Only
so it
x1
is
is
hello. It is like here it is minus x1, na? 2x1. Here it is minus. Actually, here it is minus. No? Is minus x2. From here, it is minus x2. So this comes out to be theta of, sorry for the mistake. Let me write it down again. It is 4 of theta square minus of x1 theta minus of x2 theta. Again, it goes there in plus, na? There is 4 actually. Sorry. There is 4 is there, na? 4 times of this. 4 times of x1 theta, 4 times of x2 theta, plus x1 theta, plus x2 theta, and then plus of 4x1, x2. Now it is correct. Okay. So it is 2 theta square minus 3 x1 plus x2 theta plus 4 x1 x2 equal to 0. I think up to this point it is correct now. It is a quadratic equation in theta. So the value of theta is minus of b minus b plus minus root of b square, which is equal to 9 x1 plus x2 whole square minus 4 into a into c, that is 4 into a into 4x1 x2 c upon twice of a, that is 2 into 2. This comes out to be 3 of x1 plus x2 plus minus of root of 9 of x1 plus x2 square. It is minus of 442, that is 32 x1 x2 whole divided by 4. So this is our likelihood for theta. Okay, you may also solve this in more general form, but this is the case. If we have the value of x1 and x2, then we will put the values and solve this numerical value of theta as well. Okay. Anyone have any doubt till this? Hello.
no, sir.
Okay, then if anyone have any doubts, please ask, because I have completed this tutorial. Or we can then conclude here if no question is there. Anyone?
No, sir. Thank you.
Okay, thank you. Okay, then let me stop the recording.
Hello, sir.
Hello.
Which textbook we have to follow, sir, to cover more examples?
What?
Which textbook we have to follow, sir, to cover
Uh,
more examples?
Actually, I'm not clearly. You're not clearly audible. Please. You want some more example?
Which textbook you have to prefer, sir, for practicing
Okay.
more?
Science book. Okay. You want book actually
Yes, yes, textbook.
for this. Okay. Sir has already told, na, like statistical inference by Casella Berger book is there, or you may use some some papers is also some PDF questions also there on internet. I have also searched there as the question and write down like this. Okay. If you want, please mail me. I will give you some books. Okay.
Okay, sir. Okay.
Okay then. Anyone else? Okay then.
Thank you, sir.
Okay. Thank you. Okay then.